You remember this slide, except it's different this week. Last week we only had 1,901 planets. We have 1,906 planets this week, orbiting 1,202 stars. So one of my points this 6-week semester is that the number of planets that astronomers know about, the rate at which we're discovering planets, is phenomenal. And the number of planets we know about is increasing very, very rapidly. One of the predictions I made in the book that really triggered this course is illustrated in this slide that I've used a number of places over the last year. And all you really need to pay attention to is the column on the right-hand part of the slide, in which I've got the number of planets we knew about once upon a time and then my prediction. So in 1990, we knew of exactly 0 planets around other stars. In 1995, that first planet around another star like the Sun was discovered. So we knew about 1. By 2000, astronomers who had gotten into this game of looking for planets around other stars had discovered 50 planets in total around other stars. A pretty dramatic increase, 50 planets around other stars. By 2005, that number had increased to 150. So you can do the math. 150 divided by 50 is 3. So the number had tripled in 5 years. By 2010, astronomers knew of 400 planets around other stars. Now you have to be an astronomer to do the math, because if you divide 400 by 150 and you're an astronomer, that's 3. Okay. So the number had tripled again in 5 years. And this is when I started paying attention. And I said, can that number keep tripling? Well, let's make a prediction. If the number triples again from 2000 to 2015, tripling 400, we'll have at least 1,200 planets in 2015. 1,200 planets. And what do we have this year? 1,906, and it's March. And actually, it's April, isn't it? All right. So it's already April 1st. We have 1,906 planets. We're not going to be at 1,200. We're going to be way over 2,000 planets before this year's over. And if the number tripled again, by 2020, we'd have 3,500 planets. And by 2025, 10,000 planets. And by 2030, 30,000 planets. And by 2035, 100,000 planets. And by 2040, 300,000 planets. And by 2045, 1,000,000 planets. Is that possible? Can that number keep tripling like this? Well, I showed you last week that the Gaia mission is expected to discover as many as 50,000 planets in the next few years. And those are only Jupiter-like planets beyond the Earth's distance from the Sun out to about 9 astronomical units from their stars. They're not even going to discover Jupiter in Jupiter-like orbits, let alone hot Jupiters. They're going to miss an awful lot of Jupiters, and they're not going to find Earths. And then there's the TESS mission, which is going to find tens of thousands of Earth-like planets that are near the Sun. We're not even looking far from the Sun. I think these numbers are gross underestimates of what astronomers are actually going to find. Which means well, we're all old guys, right? So maybe not in all of our lifetimes, but in our children's lifetimes and in our grandchildren's lifetimes, these numbers are real. In this century, we are going to have catalogs, phone books, with the addresses and phone numbers of millions of planets around other stars. We really will. We know where they are. We know where to look. Millions of planets. Which means the idea about thinking about life around other stars has come. Carl Sagan said this a generation ago. The idea of extraterrestrial life is an idea whose time has come. He was just a little bit ahead of his time. The time has now come to talk seriously about life in the universe, life beyond the Earth, because we know where to look. The question is, what do we look for? With these planets, we're not talking about listening for signals of extraterrestrial intelligent beings broadcasting radio messages to us, because we're looking at the planets to see what they look like. So this is not what we're talking about. What we're talking about in studying these planets is more like this. This is an actual picture of the moon Enceladus. This is a moon of Saturn. And what you're looking at are water geysers erupting off of the surface of this moon. And if there is life in the liquid oceans that exist beneath the surface of this moon, the evidence of those life forms would be in these geysers, in the light that we see reflected and emitted from the water erupting from that surface. We don't have to go to Saturn or to Saturn's moon, Enceladus, and drill a hole into the ice to see if life is there. We just need to look at the light coming from those geysers. And this is really amazing. This is Yellowstone Park erupting on one of the moons of Saturn. And all we have to do is look at the light. Now, I don't think there's likely to be life there, though some of my colleagues think there's a good possibility of it. But we can test it from Earth. We can look at the light in this top panel. You see a little planet next to a star. And we look at the collected light from the star plus the planet, and we get what's called a spectrum down here. It's the composite spectrum of the star plus the planet. And then we wait for this planet to go hide behind the star. And we get a spectrum of the star. And then we subtract the star spectrum from the composite spectrum, and what's left is just the planet. It's just the spectrum of the planet. And if that planet has life, we'd see the evidence of the life in the spectrum of the planet. If we lived on the other side of the Milky Way and we pointed a telescope back at the Earth or the Earth-Sun system and did this and got a composite spectrum of the Earth plus the Sun, and then waited for the Earth to go hide behind the Sun, and got a spectrum of the Sun, and subtracted the Sun spectrum from the Earth plus the Sun, and all that was left from the Sun, what would we see in the spectrum of the Earth? We would see oxygen. We would see ozone. We would see an enormous amount of methane. We would see the signatures in the spectrum of the Earth's atmosphere that says there is life on the Earth. We don't have to go there. We just have to look. So we could prove that life exists on the Earth just by pointing a telescope at that planet and studying the light from that planet. And we have the addresses of 1,906 planets now, and we will soon have the addresses of millions of planets. And in this century, astronomers are going to study those millions of planets. So we will soon collect a tremendous amount of evidence that will tell us about whether life appears to be present in the environments of most of those planets. And when we do that, we will find out whether life is out there or not. Now, a couple of people who look like the same person said something fairly similar about this. So Buckminster Fuller said, sometimes I think we're alone, sometimes I think we're not. In either case, the thought is staggering. And Arthur C. Clarke said, two possibilities exist. Either we are alone in the universe or we are not. Both are equally terrifying. So I don't know whether we should be staggered or whether we'll be terrified. But we should be one or the other or both, because we may soon find out whether we have company or whether in a significant portion of the Milky Way galaxy at least, we're alone. Instead of simply speculating about it, as we speak, astronomers are turning this Is it possible that life could be different from this? Yeah. How do we know what life is? So that leads me to my next slide. Okay. Thank you for the question. I mean, that's the obvious next question. Could life be different? What is life? How would we know it if we saw it? Must it be like life on Earth? We know what life looks like on Earth, sort of, maybe. Do we? I mean, we know these things are living creatures. But do we even know how to define what living things are? That in itself is a hard thing to do. So let's at least try to do that before taking on the periodic table and deciding, well, could life be based on radon? If you want to do that, let's see if we can define what life is. It's not easy. Truly, it's not easy. It's obvious what life is. It's not obvious what life is. And there are probably some biologists in here who know what life is, and we can have that argument after class. All right. Living things grow. Living things reproduce. I think most biologists, philosophers, anybody else who wants to try to define life likely would agree that whatever this living thing is would be something that grows and reproduces. Well, all right, flame, crystals, they grow and reproduce. But I don't think any of us would argue that a flame is alive or that a crystal is alive. But they do grow and they do reproduce. So those might be necessary conditions, but they're not sufficient. So what does it mean for something to be alive? Here's some other things. We've got a virus on the left. And I've got some sunflower seeds. I think they're sunflower seeds on the right. Viruses grow and reproduce, but they can't do that on their own. They need a host. They need a host cell for raw materials, for the energy, for the biochemical pathways and activities that allow them to grow and reproduce. They can't do it on their own. So are viruses alive? They are somewhere in between alive and dead. And I think biologists continue to argue about what in the world viruses are. But it's not obvious that they're alive. It's also not obvious that they're not alive. They're somewhere in between. Seeds, what are they? They don't grow and they don't reproduce on their own, but they certainly have the potential to do it. So what are they? What else can we do to figure out life? Is life a flow of matter and energy? That's more physicky. Okay? A flow of matter and energy. But it actually gets us somewhere. Living things gather and store energy. Living things definitely gather and store energy. But they do more than just gather and store energy. They organize it. Living things take in matter and energy from the outside and organize it. They organize matter and energy. So this is a cell. When I grabbed this image, I thought, I'm glad I took biology 40 years ago. Because when I studied a cell, it had a cell wall and it had a nucleus, and it didn't have a whole lot more. So somehow in the last 4 decades, cells got a whole lot more organized. There's a lot of stuff in there. Cells are incredibly well organized. That energy and matter comes in from the outside and gets structured and organized, and life does that. It just doesn't just take it in. It sorts it and it organizes it. It does that with DNA molecules too. It arranges the chemicals in certain ways. Life does more than just take in the energy. It sorts it and it organizes it. It creates information. That information is stored in the arrangements of the chemicals. So, organizing energy is a way of creating and storing information, and life does that. And when you store information, you reduce the amount of uncertainty you have. So somehow life involves reducing uncertainty in the environment, which again has something to do with physics and entropy, and we're not going to go down that road in physics, but you see where it takes you. There are complex things in the universe. Planets, stars, galaxies. Galaxies are really complex places. I mean, this image is 17 megabytes, so it's a really complex place, right? There's a lot of energy stored in the galaxy. But life isn't just complex. Life isn't just stored information. There's something more to it. It's organizing that information, organizing that energy to create information and reduce uncertainty. Leslie Orgel, who wrote a couple of books, The Origins of Life on Earth, The Origins of Life, Molecules and Natural Selection, spent most of his career thinking about life and the origins of life and what life actually is. And he wrote this quote to try to define what life is. Living organisms are distinguished by their specified complexity. By their specified complexity. They're not just complex, but they're complex in specified ways, by how they organize the energy and the chemicals. That's what he meant by specified complexity. But that's probably not quite enough. In English, this guy, Chris Impey, who wrote this book, Living Cosmos, from whom I got a lot of the information for today's talk, he wrote it more in English that I can understand here. Individual organisms utilize energy, organize matter, and store information, but they also reproduce and evolve. So that takes us back to where we started. and puts all these pieces together, it doesn't tell us that living things have to be based on carbon. They don't have to look like those orchids and elephants we started with. They don't have to be based on liquid water flowing through them. This is about something different. It's about energy and matter and the storage of information and about reproducing and evolving. Interesting. If you want to try to come up with a different definition of what living things are, good luck. Let me know what you come up with. It's hard to do. Where do we go from there? What can we learn from life on Earth? We can look at life on Earth and see if we can figure out what it is we might be looking for or thinking about when we look beyond the Earth. Because again, life doesn't necessarily have to be exactly the same elsewhere as it might be on Earth, but maybe we can figure out something about life in the universe from studying life on the Earth. So what can we learn from life on the Earth? On the Earth, all of life is built on one molecule, the DNA molecule. You will not find any living thing on Earth that doesn't depend on DNA. Now, that doesn't mean that all life in the universe has to depend on DNA. But it strongly suggests that all life on Earth has the same root. That life on Earth didn't emerge multiple times from multiple different pathways, but that a single mechanism, a single pathway for life that built on this DNA molecule was successful and branched out to form all the different kinds of life forms on Earth. That this DNA molecule is a pretty tough little beast and is the basis for all life on Earth. It doesn't matter whether it's in the air or deep in the ocean or on the land, animal, vegetable, it's DNA. The DNA molecule is made from only 5 elements. We're going to look at the periodic table. Like it or not, you're going to look at the periodic table in a few minutes. The periodic table has lots of elements in it, but only 5 of those elements are in the DNA molecule. Hydrogen, carbon, oxygen, nitrogen, phosphorus. You don't need anything else for a DNA molecule. Hydrogen, carbon, oxygen, nitrogen, phosphorus. 5 elements. That's it. Those must be important elements. In life on Earth, in that orchid, in that elephant, in that amoeba, there are a few other elements that are used. Sulfur, sodium, fluorine, potassium, calcium, iron, magnesium, chlorine, iodine. There isn't much else. There are a few other elements. You can go and get your 50-plus vitamins and look and see what else there is, but there isn't much else. There are a handful of other elements, other trace elements that are important, but they're trace elements. These are 99.9999% of everything in you. Not much. So here's your periodic table. Now we're back to, I don't know, 7th, 8th, 9th grade chemistry class, whenever you first took chemistry. And here's your periodic table. You've got hydrogen in the top left, and helium, and lithium, and beryllium. And for each of these, the element has a name, and the element has an atomic number, and the element has an atomic weight. And for those of you who need the reminder, hydrogen is atomic number is 1 because it has 1 proton at the center. It's got an electron that orbits the proton, and we're going to look at this the simple old-fashioned way in which an electron is an actual particle orbiting the nucleus. In modern sense, the electron is a probability cloud that orbits the nucleus, but let's not go down that path, okay? So we have an electron orbiting the proton. For helium, there are 2 protons in the center and 2 electrons orbiting the nucleus. For lithium, lithium-3, there are 3 protons and 3 electrons. For neon, there are 10 protons and 10 electrons. You get the picture. That's your periodic table. And we have hydrogen. It's the simplest element. And helium. And helium wasn't involved in DNA or in us. And lithium wasn't involved in us. And beryllium wasn't involved in us. And boron wasn't involved in us. But carbon and nitrogen and oxygen was. And fluorine was. And neon wasn't, etc. Most of these elements have nothing to do with life. There are a lot of elements here. Most of these are not involved in us. That must tell us something. But they exist in the universe. That must tell us something. You can hypothesize all you want about life in the universe and what life might be made of. But maybe there's a message in what life is made of on Earth about what's here. Now, life on Earth is based on carbon chemistry. Carbon's right here. And those of you who took organic chemistry, that was all about carbon-based chemistry. Carbon's very versatile. It combines with lots of things. So lots of people have speculated, and science fiction writers have speculated about silicon-based chemistry, because it's right under carbon here in the periodic table. Well, of course, our computers are silicon-based. So maybe you could just swap out silicon for carbon. It doesn't seem to work all that well, because when you bond things with silicon, the silicon doesn't actually want to let go. So silicon-based chemistry is not as versatile as carbon-based chemistry. But you can have those conversations and try to come up with other elements in the periodic table which could be as chemically adaptable and flexible as carbon. And maybe there's something that could do it. But the further down on the periodic table you go, the less of that stuff there is. So it would be harder to make living things when there's less stuff available. There just isn't very much Rutherfordium around. You want to make life out of Rutherfordium, good luck, but there's just not much of it. You could also speculate about making life that's not based on chemistry. It's not based on the elements. Maybe you could have life that's made out of magnetic fields. You can speculate all you want, but I don't know where we go with that. But it's possible. But we, right now, don't know how to have much of a conversation about it. What we know how to do is to talk about what we can see on the Earth and what we can learn from that. And that's about all we can really do right now. So life on Earth is based on chemistry, and it's based on just a few things on that periodic table. Looking around us, we can look at the sun, our neighbor. The sun, by mass, is made mostly of hydrogen. 70% of the mass of the sun is hydrogen. 28% of the mass of the sun is made of helium. 1.5% of the mass of the sun is made of carbon, oxygen, and nitrogen. The last 0.5% of the sun is made of all the other stuff. Well, what are we made out of? Hydrogen, carbon, oxygen, nitrogen, phosphorus, and some of the other stuff. We're not made out of the helium, but that's pretty good. We're made out of the dominant stuff in the solar system. The sun is made out of pretty much the same composition as every other star in the universe. And the stars are made of the same composition of all the galaxies in the universe. This is what the universe is made of. The entire bloody universe is made out of about 70% hydrogen, high 20% of helium, and 3 to 5%, depending on where you are in the universe, of all the other stuff. Life on Earth, ignoring the helium, is made out of the dominant chemical stuff in the universe. That's a pretty good clue, if you will, that if life is on the Earth is a good message, that the universe has plenty of stuff out of which to make life in other places. Helium's an inert element. It doesn't combine with other stuff. It's no good for chemistry, so you just ignore it. We are made out of the dominant stuff in the universe. So maybe life could be abundant out there. It's made out of the same stuff. The stuff is out there. What about the Earth? We live on the Earth. We're not made out of what the Earth's made of. We're made out of what the sun's made of, and we don't live on the sun. We live on the Earth. The Earth, 35% of the Earth is made out of iron. Most of that iron is down in the core of the Earth. But a good third of the Earth is made out of iron, and we're not made out of iron. 30% of the Earth is made out of oxygen. We're actually made out of a good bit of oxygen, the water in the oxygen in the water. 15% of the Earth is made out of silicon. We're not made out of silicon. 13% of the Earth is made out of magnesium. And then there are a bunch of other important elements in the Earth: nickel, sulfur, calcium, aluminum. We're not made out of the Earth. What we are made out of is not representative of what the Earth is made out of. So we ought to be living on the sun, not on the Earth. It's a little puzzling. But we do live on the Earth's crust. We're not living on an aggregate that's a mixture of the entire Earth, and the crust of the Earth isn't made of exactly this. The crust of the Earth has lots of water and lots of carbon. The crust of the Earth looks more like what we're made of rather than the entire Earth. Again, there's a message, but the message is you need the right environment with the right elements in the right places. The sun's a little bit too hot for us. The Earth as a whole is made of the wrong stuff, but the surface of the Earth has the right temperature with the right stuff. So maybe you have to have the right environment with the right stuff. Where do you find that environment? Well, the universe kind of started with a big bang. And all this stuff came flying apart, forming the universe, expanding. In cartoon fashion, here's our Big Bang. What you're looking at here is time, effectively, from left to right. So the universe starts with this Big Bang on the left and expands going to the right. And as time proceeds going to your right, stuff happens in the universe. So the first thing that happens in the history of the universe is energy forms matter. And the matter that forms are the elements. But the elements that form initially are not all the elements in that periodic table. Because during the first few moments in the history of the universe, the only elements that could form were hydrogen and helium. And that means that when the first stars were forming right here, the first generation of stars, they could only be made of hydrogen and helium. There was no carbon. There was no nitrogen. There was no oxygen. There was no iron. There was no magnesium or nickel. There could be no Earths. There could be no us. For some amount of time during the history of the universe, there was no possibility of life, unless that life could be made only from hydrogen and helium, or unless that life is made of magnetic fields or electric fields or something else. If the life was based on chemistry, unless life could be purely made of hydrogen and helium, and I think that's pretty doubtful, there was no possibility of life existing in the universe for some amount of time. What was that amount of time? We can only speculate about that. But for some amount of time, until the first, second, third generation of stars, until the first generation of galaxies had enough time to produce what we call heavy elements, we could not exist. Because the first generation of galaxies would not have had enough oxygen or carbon or nitrogen or iron or anything else. So for some amount of time, from the birth of the universe onwards, the universe had to be devoid of life. The universe was uninhabited for some amount of time. At some point in the modern universe, the right-hand side of this, we're over here on the Earth with our telescope looking back in time. At some point in the history of the universe became habitable. Life became possible. We don't know when that was. We can only speculate. But the first generations of galaxies don't have the stuff in them in which life could exist. There are galaxies in the universe known as elliptical galaxies. Elliptical galaxies are old galaxies. Elliptical galaxies, they look elliptical, right? They don't have spiral arms like the Milky Way, like our galaxy. There are spiral galaxies and elliptical galaxies. Elliptical galaxies, there are lots of them. Elliptical galaxies have lots of stars in them. The stars in elliptical galaxies are old stars. Elliptical galaxies don't have any young stars in them. All the stars in elliptical galaxies formed a long time ago. Elliptical galaxies formed a long time ago. There could be planets in elliptical galaxies orbiting some of those stars. But those planets are going to be made of hydrogen and helium and nothing else. The chances of there being any living things on any planets in elliptical galaxies is pretty much zero. We don't need to worry about or look or try to study or think about life in elliptical galaxies. Question?
And we know this because studying the spectra of those older stars?
We know this. How do we know that elliptical galaxies are old? That's effectively the question. Because elliptical galaxies have no young stars. They only have old stars. Stars which are 7, 8, 9, 10 billion years old.
But we know their composition.
And we know their composition by studying their spectra. And their composition says they are very, what astronomers would say, they're very metal poor. They don't have very many heavy elements. They're very metal poor. So chances are very, very slim that elliptical galaxies are good places for life. We can pretty much cross them off the list. What we need to focus on are spiral galaxies. We live in a spiral galaxy. The Milky Way is a spiral galaxy. Spiral galaxies generally are younger than elliptical galaxies. Spiral galaxies have younger stars than elliptical galaxies. Excuse me. In the spiral arms of spiral galaxies, young stars are forming. New stars are being born. New generations of stars are being born over and over and over again, and this has happened for the entire lifetime of the spiral galaxy. So 10 billion years ago, 9 billion years ago, 8, 7, 6, 5, 4, 3 billion years ago, new stars have been forming. And when those new stars form, inside those stars, they make the carbon and the oxygen and the nitrogen and the phosphorus and the calcium and the magnesium and the iron And when the big stars die, they blow up. And when they blow up, they eject those materials out into the interstellar medium. And those materials then get collected into interstellar clouds in which new stars are born. And when those new stars are born, planets are born. And the planets that are born around those younger stars, those planets can form out of the heavy elements. They can have iron and calcium and oxygen like the Earth. Yes? How do the stars in elliptical galaxies die? Most of the stars that remain in elliptical galaxies are little stars. And when they die, they turn into white dwarfs. They don't blow up. They just sort of fade away and burn out. Yes?
Why is it that these like this are in a spiral shape?
Why do spiral galaxies have spirals? Astronomers have been arguing about that forever. And we have theories to explain it. There are things called density waves that propagate through these spiral galaxies that sort of re-energize these spirals. I don't think you want to go down that path today. Okay? Okay. It's complicated. That's unfair. I'm not sure we actually do agree on exactly why they have spirals or what triggered the formation of the spirals in the first place. And it may have been collisions of elliptical galaxies that triggered the formation of spiral galaxies originally, but we don't actually know that answer. We just know that we have some spiral galaxies and we have some elliptical galaxies, and spiral galaxies are the ones where stars form, and elliptical galaxies are effectively dead galaxies. New stars are not being born. Earth-like planets don't exist in elliptical galaxies.
I think the closest star to our sun is Alpha Centauri, about 4 light years
Yes.
away. And looking at a wonderful spiral galaxy like this, what is the average distance between these stars?
Okay. Question started with Alpha Centauri is the closest star. It's about 4 light years away. What's the average distance between stars? The average distance between stars is a few light years. In this picture, that spot, that red spot on the diagram is way, way, way bigger than that distance. The distance from about the edge of this picture to the center is about 30,000 light years. The sun is about a third of the way from the center of the Milky Way galaxy out to the edge. So the sun is maybe about here relative to this distance in our galaxy. It's a big place. And of all the planets that have been found so far that we're talking about, we are probably talking about the size of the spot by laser pointer. We haven't surveyed a very big portion of the Milky Way galaxy. We've only surveyed within about 1,000 light years, which is nothing. Yes?
When we look back in time through our telescopes, how far back can we look and see the heavy elements?
When we look back in time through the telescope, how far back in time can we see the heavy elements? When we look through our telescopes, we can see back to the beginning of the universe, or within a few microseconds of that. So that's 13.7 billion years ago. So that's the first part of the answer. We can't see that much detail. We can't see as much detail of what we're seeing 13.7 billion years ago as we can see 1 billion years ago. The further back we get, the less light we collect, the less detail we have. So when we're looking at things that are closer to us in space and closer to us in time, we get more light, we get more detail, we know more. But we know a fair amount even about those very distant things. We know enough about the things that are 6, 7, 8, 10 billion light years away that we know that they're dominantly made of hydrogen. And we don't see the spectral signatures of much else. If they had lots of iron, we think we should see that. We think we have the sensitivity to see those signatures. We don't see those signatures. There will be bigger telescopes soon. They will collect more light. If the stuff is there, we'll see it. Yes? Is there any evidence that the universe is elastic so that the expanding universe will then collapse again? No. At least not this week. Okay? Okay. At the moment, it appears that the best evidence we have is that the expanding universe is expanding faster and faster and faster, what's referred to as the accelerating universe. When I was an undergraduate, the universe was going to expand and bounce back, but we don't think that's the case anymore. The evidence doesn't seem to support that. Yes? Are these galaxies spinning? Yes, spiral galaxies spin. What's at the center? Most spiral galaxies, although it looks really bright at the center, spiral galaxies all have bright halos at the center as we see them. At the very, very center, almost all spiral galaxies have black holes. And those black holes, even the Milky Way has a black hole at the center. You would think if there's a black hole, there'd be a dark spot at the center. But a picture like this doesn't have the spatial resolution to see that. The black hole is very, very tiny. So you can't see the evidence of that in this kind of picture. Yes? How many spiral galaxies are there? A few hundred billion. All right. We've talked about the concept of a habitable time in the history of the universe. The first few billion years of the history of the universe was uninhabitable because there was nothing out of which life could have been made. And that leads to the idea that there are certain galaxies in the universe that are uninhabitable, at least from a chemical standpoint, because they're not made of the right stuff. We can now talk about the Milky Way galaxy or spiral galaxies in general having habitable zones, what's referred to as the galactic habitable zone. The green part of this image is, in cartoon form, the galactic habitable zone. Whether this concept is right or wrong depends on which astronomer you talk to and how strongly they believe these ideas, but the ideas are worth talking about at least. In the center of galaxies, well, let's start on the outside. The outside of galaxies, even like spiral galaxies, there may not be enough stars being formed. The rate of star formation may be so low that there may not be enough heavy elements, carbon, nitrogen, oxygen, calcium, magnesium, etc., for Earth-like planets to form, for Earth-like chemistry, biology to happen. So there may be a zone in the outer part of a spiral galaxy where we don't have enough elements heavier than hydrogen and helium for life like Earth-like life to exist. So this outer part of a spiral galaxy might be like elliptical galaxies. It might be uninhabitable. Maybe. The inner part of a spiral galaxy might be uninhabitable for an opposite reason. The rate at which stars form might be so rapid, and the number of massive stars that form might be so large that the inner part of the galaxy might be uninhabitable. Those massive stars don't live very long. And when they die, It's not good for anybody who's nearby. Because when they die, they blow up as supernovae. And when they do that, they spit out lots of gamma rays and lots of X-rays and lots of super high energy particles. And if you're in the environment near that star meaning maybe within a few thousand light years, and we just said the average distance between stars is maybe just a few light years. So if you're within a few thousand light years of one of these supernova explosions, maybe life was getting started on your planet. Well, your planet just got sterilized. And if it's tough for life to get started and get going, you don't want life to get sterilized all that often because you might not get another chance. So the inner part of the galaxy might be uninhabitable, or it might be habitable for such a short amount of time that life could never evolve and become advanced. So some people think that galaxies might have a sweet spot, a galactic habitable zone. Whether this is a strong concept or a weak concept depends, again, on who you talk to. But it's an interesting concept to debate. All right, so here's our inner zone, which is too violent. Solar systems might also have habitable zones. This is a concept which is much better understood and not debated at all. It's just a question of exactly where this habitable zone is. So this is a cartoon of our solar system. The sun is off the picture to the left, and we have Mercury, then Venus, then the Earth, then Mars, then Jupiter, Saturn, etc. And there's a sweet spot in our solar system, illustrated by the little ring here around the Earth. We know the Earth is habitable. The question is, how much of our solar system is habitable? There's a concept known as the Goldilocks zone. Pretty obvious what that means. If you're too close to the star, it's too hot. If you're too far from the star, it's too cold. This specifically refers to the idea that life depends on water, liquid water. Life, as we know it on Earth, depends on chemistry which is mediated by the presence of liquid water. Chemistry goes much faster in the presence of a liquid medium. The liquid that does that in life on Earth is water. Water is a very abundant liquid, and at the pressures and temperatures at the surface of the Earth, water is in the form of a liquid. That's pretty good for us. But if it gets too cold, water freezes. If it gets too hot, water evaporates. So if you get too close to the sun, the water evaporates. Venus doesn't have any water. Venus is too close to the sun. And it's a long song and dance to talk about why Venus doesn't have any water, but Venus almost certainly once did have water. Venus is 95% the radius of the Earth. It's 82% the mass of the Earth. Venus is very Earth-like. And Venus probably started with a very similar amount of water as the Earth. But Venus is dry. The temperature on Venus, the surface temperature of Venus, is about 900 degrees. There's no water. It's evaporated. And not only has it evaporated, the sun has blasted the atmosphere of Venus so that the water has been effectively like sandblasted off into space. It's gone. It's not just in the atmosphere. It's gone. Venus is dry. It's too hot. If you get too close to the star, it's too hot. Even if you start with water, you can't keep your water. If you get too far from the star, the water freezes. And you turn into ice. And then chemistry's tough. So we are in the Goldilocks zone. The question then becomes, how broad is the Goldilocks zone? And this is actually a pretty complicated question. Stars are different. So this illustration has 3 different stars with planetary systems around the stars. The sun is known as a G star. Astronomers have classification systems for stars with which we use an alphabet system. There are O stars, which are the most massive, hottest stars. The sun is a G star. A stars are a little bit hotter than the sun. M stars are cooler than the sun. If you're cooler than the sun, then in order to have the same temperature as the Earth, that planet would have to be closer to the star. So the habitable zone for an M star is closer to the star than for a star like the sun. For an A stars are hotter than the sun. So if you're the same distance as the Earth is from the sun around an A star, you're going to be hotter, maybe too hot. So if you're orbiting an A star, you have to be further from the star in order to have the same temperature that the Earth has. So the habitable zone around an A star is further away than the habitable zone around the sun. So the habitable zone around a star depends on the type of star. The habitable zone around a star also depends on the age of the star. When the sun was young, it was not as hot as it is now. As the sun gets older, the sun warms up a little bit. Not by a lot, but by a measurable amount. Now that doesn't mean next week the sun's hotter. I'm talking about over billions of years. But the Earth has been here for 4.5 billion years. So 3.5 billion years ago, the Earth was not warmed as much by the sun as it is warmed now. So if the Earth had the same temperature 3.5 billion years ago as it does now, the Earth's atmosphere had to help make that happen. In a billion years, the sun will be warmer than the sun is now. The habitable zone will move around a star. But the Earth doesn't have retro rockets on it, so you can't actually move the planet. So depending on where a planet is, a planet may start in the habitable zone. It may start with liquid water and then get too hot. Venus might have started in the habitable zone and then it got too hot where Venus was. So in talking about the habitable zone, we need to wonder, how long can a planet exist in the habitable zone? Can it exist for long enough for life to develop? These are some cartoons of habitable zones around known planetary systems. The Kepler-22 system has one planet, we think probably just on the inner edge of a habitable zone. The Kepler-62 system has 2 planets, we think, in the habitable zone. The Kepler-69 system with a planet in the habitable zone. The Kepler-47 system with a planet in the habitable zone. And even if the planet, let's say Kepler-47c, is a giant Jupiter-like planet in its habitable zone, Kepler-47c might have an Earth-sized moon in orbit around a Jupiter-sized planet in that habitable zone. That could be an interesting place. Bottom line is, we have found some planets already that are in the habitable zones around their stars. But it's not as simple as saying, oh, that planet is the same distance from its star as the Earth is from the sun. It depends on the temperature and the size, the mass of the star to know where the habitable zone is. Yes?
When a planet is found in the habitable zone, so it's worthy of assuming a further study, what does that further study look like?
That further study, for the most part, is down the road. But future astronomers are going to try to isolate the light from the planet in order to do the sorts of things I mentioned early, to try to look at the light from the planet and look at the spectroscopic signatures of the light from the planet to start looking for molecules in the atmosphere of that planet. Does that planet show evidence of oxygen or ozone or methane, ammonia, the sorts of molecules that we currently know how to detect? The first step is simply, can we isolate the light of the planet from the star? Step one. Then, what can we learn about the atmosphere of the star? Can we measure, or the planet? Can we measure the temperature? Can we prove it has an atmosphere? What's in the atmosphere? What's the density of the atmosphere? What's in the atmosphere? All right. Something different. I want to tell you about a meteorite, a famous meteorite, perhaps the most famous meteorite. Allen Hills 84001. It's a meteorite from Mars. It's also sort of a meteorite from Antarctica. It also looks like this when you cut it in half. This little block down here in the corner is 1 centimeter. So it's not a big hunk of rock. You could put it in your pocket if your pocket was big enough. In a slice through that meteorite, looking through an electron microscope in 1996, some folks found this worm-looking thing. The one in Antarctica. And they said, that looks like a worm. They said, this is evidence that this Martian meteorite had life in it. It's a fossil remnant of life from Mars. And this proves that Mars had life on it once upon a time. This is, as my caption says, disputed, to say the least. How did it prove the meteorite was from Mars? Really good question, which leads me to this slide. All right. What do scientists agree on? I'll try to answer that question. This rock formed on Mars about 4 billion years ago. Okay. How do we know that? We know that from the radiometric dating of the materials in the rock. And in the rock, there are little bubbles of gas, trapped gas bubbles. The gas in those bubbles were trapped when this meteorite was heated and knocked off the surface of Mars by a meteorite impact. That meteorite impact occurred 17 million years ago. When this meteorite was heated 17 million years ago, it was not melted, so parts of it retained the radiometric age from the lava that formed it 4 billion years ago. But parts of it remelted, which gave it a radiometric age of the 17 million years. And when it remelted, it flew through Mars's atmosphere and collected some of the gases from Mars's atmosphere. And those gases were trapped in those bubbles. And those gases never got out until some scientists stuck a needle in and pulled the gases out. And the gases in those bubbles match what are called the isotopic ratios of the gases in Mars's atmosphere. And they don't match the isotopic ratios of the gases in the Earth's atmosphere. In the Earth's atmosphere, we've got oxygen. But oxygen can be oxygen 16 or 17 or 18. And Mars has oxygen 16, 17, and 18 in the oxygen and the carbon dioxide molecules in its atmosphere. And those isotopic ratios of oxygen are unique to Mars's atmosphere and Earth's atmosphere and Venus's atmosphere and the rocks on the moon. These are fingerprints of the different planets and places in the solar system, and these are fingerprints of Mars. That's how we know this thing is from Mars. This thing landed in Antarctica 13,000 years ago, and in 1984, the National Science Foundation sent people to Antarctica to hunt for meteorites, because meteorites are easy to find in Antarctica because it's ice. And if you find a rock on the top of the ice, it probably fell from the sky. And they found some meteorites, and they put them in their pocket, and they brought them back to the United States, and it turns out that one of them is from Mars. Just this one. But since then, other meteorites have been identified that are from Mars, and some have been identified that are from the moon. But this one is the one that triggered all the hoopla. Not everybody agrees that these chain-like structures are microfossils. I don't think they're microfossils. The folks who wrote the first paper in 1996 still think they're microfossils. I'm not sure anybody else does, but they still do. What's most important, I think, about this meteorite is that it launched the entire field of astrobiology. And one of the things it did is it triggered a search for what are known as extremophiles on Earth, which has expanded our knowledge of what life can be like. So we have found Bacillus infernus, the bacillus from hell. Okay? It can live at temperatures up to 122 degrees Fahrenheit. Discovered in a deep drilling project in Virginia. Pretty fancy looking guys here. Okay? It does not do photosynthesis. It doesn't breathe oxygen. It's anaerobic. It does not consume any organic materials. It breathes iron and manganese oxide. And it divides very slowly, once per 1,000 years. Weird creature. Okay? Here's the creature known as strain 121. It survives at temperatures up to 250 degrees Fahrenheit. It's found in these deep sea vents just off the coast of Washington State and Puget Sound. It's the champion hydrothermophile, as it's known, heat-loving bacterium, 250 degrees. This suggests that this idea of the habitable zone maybe should be expanded a little bit. Maybe not for you and me, but for these guys. Deinococcus radiodurans, Conan the bacterium. Okay? It can withstand radiation dosages thousands of times what we can handle. It's got 5 different copies of DNA that's ready for transcription, so it can repair its DNA very, very quickly. It's got a really tough layer of lipids to survive the vacuum of space. Tough little bugger. Okay? Dunaliella salina. It can handle salinity 10 times greater than ocean water. This is so great that the salt just precipitates out of this stuff. Okay? It's found in sea salt fields. It's a great antioxidant. And in fact, you can get supplements at the local grocery store made from this stuff. It's used in cosmetics as a great source of beta-carotene. Okay? Ferroplasma acidarminus. It's found in the Iron Mountain mine in Mount Shasta. This is the really nasty iron runoff from Iron Mountain. This picture is 1 meter across. This is what's called the biofilm, the living junk flowing out of there. This is one of these archaean bacteria. It grows best at a pH of 1. Now we're back to your chemistry class that you don't remember. Okay? It can grow at temperatures up to 240 degrees Fahrenheit. It can live at a pH of 0. pH of 0 is battery acid. Okay? Okay? Now I have down here really as my notes so I can remember what pH works as. A pH scale, each step of 1 is a factor, I should say a factor of 10, not a factor of 1. Okay? The pH of water is 7. So if you go from 7 to 6, it's 10 times more acidic. From 6 to 5, another factor of 10 more acidic. So from 7 to 1 is a factor of 1,000,000. 1,000,000 times more acidic than water. Lime juice has a pH of 2. You can use lime juice to cook fish. That's how you make ceviche. Pretty good stuff. Okay? Powerful stuff. Hydrochloric acid has a pH of 1. This stuff has a grows in pH of 1. It's nasty stuff. Okay. All right. And then there are the tardigrades. They're really cool. Okay? They're the water bears. These are not single-celled creatures. These are the water bears. They're multi-celled. They have brains. They have legs. They have nervous systems. They have sexes. There are more than 1,000 species of these guys, the tardigrades. Okay? They've been found living at temperatures as cold as minus 300 and plus 300 degrees. They can survive in the vacuum of space. They can survive at pressures as high as 1,000 atmospheres. They can go into a freeze-dried state and live in suspended animation. They can handle radiation at up to 1,000 times what humans can handle. These guys are tough. Tardigrades, the water bears. Really cool. All right. I don't know how they taste. Okay. They're found everywhere. I don't know where they're found. On the web. Okay. And then there's stromatolites. Okay. Stromatolites are the most ancient living things on Earth. These are big rocks, if you will. But they're not rocks. They are living things. Living things. Read a quote to you. Their layers were produced as calcium carbonate precipitated over the growing mat of bacterial filaments. Photosynthesis in the bacteria depleted carbon dioxide in the surrounding water, initiating the precipitation. These are algal mats, which then precipitate these layers of stuff, which then create these rock-like things. As the process occurred over and over again, the layers of sediment were created. This is a microscopic look at the archean bacteria that do this. The oldest rocks on Earth are 3.8 billion years old. The oldest stromatolite fossils found are more than 3.5 billion years old. So life on Earth got started pretty quickly. Pretty quickly. Interesting. All right. One more thing. The Murchison meteorite. There are about 100 kilograms of the Murchison meteorite that have been found. This is a little piece of it, just 42 grams of the Murchison meteorite. Why is it interesting? It was seen falling to the ground in 1969 near Murchison, Australia. 100 kilograms were collected almost immediately. 1969, most of you will remember, is the year we set foot on the moon, which meant NASA had put a lot of money into chemistry labs to get ready for these rocks that were going to come back from the moon. And the Murchison meteorite fell, and all these moon geochemists said, cool. And they got hunks of it, and they studied it. Well, this thing is a very primitive meteorite, 4.562 billion years old. It is as old as the solar system. It's a fossil of what materials were like when the Earth and the Sun and the planets were forming. In this meteorite, uracil and xanthine have been found. Well, what are uracil and xanthine? You biologists would know. In modern biology, uracil is ubiquitous as a nucleobase in RNA, while the role of xanthine is limited in modern biochemistry, most notably as an intermediate in the biosynthesis of guanosine and uric acids. This is a quote from the paper that was published in 2008 with this stuff. These results demonstrate that organic compounds, which are components of the genetic code in modern chemistry, were already present in the early system and may have played a key role in life's origins. At least one of the bases in DNA was floating around in this meteorite in the solar system 4.5 billion years ago. It didn't have to form on the Earth. It was already out there. That's neat. All right. All right. One more thing. We're almost done. You asked how far away was the nearest star. I just want to emphasize the stars are far apart. We're not going anywhere. And it's probably hard for anybody else to go anywhere. So we're going to do a little math. I'm going to do a little math. You know this equation. Distance is velocity times time. So I can divide distance by velocity and get time. Time is distance divided by velocity. So I'll do the math. I need a velocity. So I'm going to build a rocket to go to a star. What rocket do I want? I'm going to take the rocket that's on its way to Pluto. It's the fastest rocket humans have ever built. It's going 16 kilometers per second. That's really fast. That equates to about 40,000 miles an hour. But I'm going to let my rocket go faster. I'm going to make my rocket go 67,500 miles an hour, which is actually 30 kilometers per second. That's twice as fast as my Pluto rocket. It's a nice number because the math works out easy. All right. And my distance to Vega, I want to go to Vega. Jodie Foster went to Vega in contact. So I want to go to Vega. Okay? It's 25 light years away, but I need to turn that into kilometers. That turns out to be 2.37 times 10 to the 14th kilometers. I did the unit conversion for you. So now I have the numbers I need. Time is distance divided by velocity. There's my math. It's 7.9 times 10 to the 12th seconds. And you know what that means. I did another unit conversion, 250,000 years. You want to go to Vega on a rocket at 30 kilometers per second, 67,500 miles an hour? It's going to take you 250,000 years. 250,000 years. it will take, if there's any Klingons out there, it's going to take them a long time to get here. Unless they can figure out how to break the laws of physics, which I don't know how to do, it's going to take anybody a long time to colonize the galaxy. The galaxy is a big place. All right, 2 more things for you. One is next week we go down the rabbit hole. We really go down the rabbit hole. And then as you're walking out, I want to see if this works. Because, come on. It's worked earlier. It's all broken. What's wrong? Come on. I can't even make it stop. What's going on? All right. It's not working. It worked when we came in, and then I broke the system. I'll play this for you next week. Could I sing it? Whenever life gets you down, Mrs. Brown. It's about life in the universe. We'll start with this next week to get us started. Oh, well. Thanks for coming. We'll see you next week.